My name is Alex. I'm one of the co-founders of Pantograph with Kelsey over here. These are our robots. We'll talk about them later, and at the very end, we'll have a demo that I think will be fun. A subset of the people in this room will get to drive the robots. This talk is kind of an experiment. I haven't given this talk before. I couldn't think of one thing that I wanted to talk about, and so I decided to make it up in volume. And so these are 14 different ways that the future could go in futures where there are a lot of robots. I think a lot of discussions of the future are very abstract. Well, I think it's nice to counterbalance those with just some very concrete kind of images or vignettes of ways the future could be. So without further ado, that was the preamble. This is the first one. This is a thought experiment that I stole from a book that I quite like by Freeman Dyson called Disturbing the Universe. And in the thought experiment, there's a company called Rossum's Universal Robots, RUR. And the first product that they make is a boat. And the boat is mainly made out of a few different elements, carbon, oxygen, hydrogen, nitrogen. These are things that you can obtain from air and water, and in principle could be manufactured primarily with the energy from sunlight. Yes. How's this? Better, okay. All right, so we've got this boat. It's made of some materials. It can, in principle, be manufactured primarily using the energy of sunlight. And additionally, it contains within itself a small factory which is capable of making an entire replica of the boat. And so in this first demonstration, the Rossum's Universal Robots company pushes the boat out of a harbor, goes out into an ocean somewhere, and maybe 6 months later, it comes back, and now there are two boats, and two identical boats next to each other are in the harbor. They have some purpose maybe for making these boats. Maybe they collect energy, maybe they distill seawater. And of course, there's like an obvious problem with this as they start doing this. Some number of months later, there are 4 boats and then 8, and 5 years in, you can no longer traverse the oceans because they are covered with these identical boats that are distilling seawater. This is originally from an article by Edward Moore called Artificial Living Plants. We don't normally think of robots as plants, but this is such an example. Today, we obviously know a lot more about self-replicating automaton, but I think it's nice to think about these boats. It's sort of more vivid. Another example from the same article, now we're trying to move material around the solar system. Enceladus is one of the moons of Saturn. It has a lot of ice. It's one of the main sources of ice that, in principle, you might be able to use within the solar system. Still, Rossum's Universal Robots company, now we're launching, instead of a boat, a solar sailboat with a solar sail. Again, it's only a single boat initially. It goes to Enceladus. Again, it contains within itself a factory and all of the information needed to make copies of itself. And what we observe now from Earth through a telescope, let's say, is some years later, a cloud starts to form around Enceladus. And this time the robots are programmed a little bit better. They have navigation instructions to go to Mars. And some years after that, you notice that there's a cloud of what looks like ice droplets around Mars, which starts to fall into gravity, the gravity well of Mars. And some years after that, now you have a lot of water on Mars. I think this is also, a different way of imagining the way that you might move a lot of material around the solar system instead of, one big rocket and a lot of kind of manpower and energy. It's this little seed that you can send, and it acts much more autonomously. So much for space and Dyson. This is much more mundane. In the relatively near future, you might be able to buy robots for your home. Usually people think about, cleaning and making your bed and things like that. A relatively different thing that you might imagine robots being able to do at home is manufacture kind of small things that today people make DIY, but potentially with a much higher degree of quality and maybe a lot more control or flexibility from the person who wants to make the thing. You could imagine this sort of idea being combined with coding agents that are today obviously getting very good to allow people to DIY make things that are very complex that today you could not imagine anybody making themselves, like a phone or a laptop, a projector, very complicated things that normally are manufactured in factories and require a high degree of skill. I think it's interesting to imagine vibe coding a MacBook, not the operating system for a MacBook, but the MacBook itself, with a little robot in your garage that, can order materials off of Amazon and things like that. And the last thought about this is, in a way, this is going back in time. It used to be that, if you were at home, you would make your own clothes, you would spin wool and dye it yourself and things like that, which gave you a lot of control over the goods that you used in your everyday life. And so in some ways, this would kind of move manufacturing away from centralized factories, which has been the trend over the last few hundred years, back to something much more decentralized. Also in manufacturing, but a different direction. So back to centralized factories. One of the trends in manufacturing over, again, the last few hundred years has been towards economies of scale, consolidation, making one unit very simply, many, many times over and kind of squeezing out a lot of efficiency due to just so many parts of the process being shared across each unit. As robots become more flexible and cheaper and able to do more portions of an assembly process or some item, you could imagine that even centralized manufacturing could become much more heterogeneous. And you could imagine each person buying like an entirely different item from the same factory, from the same store, not just like, clicking through different colors in, a web UI or something like that, but, potentially an entirely different shape, an entirely different way that something could be. One example of this, which might be very important, could be something like vaccines. You could imagine if that's an instance where there's like a new SKU, there's a new virus that you need to make a vaccine that can, counteract the virus. And it would be very useful to be able to, at large scale, very quickly manufacture a huge amount of such a vaccine. This is further from the world that we live in, but still on Earth. City maintenance. Today, there's very little physical labor kind of per square mile that goes into the cities around us. There's some people who work for the city who do things like cleaning the streets and taking out trash some amount of the time. But as labor becomes much cheaper, you could imagine, on every square block of San Francisco, there are maybe a dozen robots whose job it is to do things around that block to keep things clean, or even do maybe medium scale construction projects. One little thought experiment here, you could imagine in a park, there's some layout to the park, there's some fixtures in the park, there are water fountains and sheds and things. You could imagine trying to measure how effective the water fountains and sheds are, maybe by how much they're used. This is some kind of optimization problem, and maybe end to end, the robots can try to optimize the locations and use of the water fountains and the sheds in the park. Mm-hmm. This is again pretty different, but I think potentially one of the most long-term impactful applications of robotics. Deep learning is an example of an area of science that has benefited a lot from scale recently. Obviously, we're scaling data sets, we're scaling compute. And those things are just directly leading to returns on the quality of the artifacts that are produced. Other areas of science, I think, are beginning to shift into regimes where they also benefit a lot from scale. Historically, you had one scientist, I don't know, Louis Pasteur, who's experimenting with bacteria in his lab, and there are limits to how much that can produce. There are limits to the number of scientists and to the amount of data that one person can process. When you have very high degrees of automation, you can imagine just at extremely large scale collecting, vastly larger amounts of data about biology. For example, I have this example of the protein data bank, which was this very important data set for the creation of AlphaFold. It's, I think, about 250,000 proteins that were painstakingly by humans imaged with, I think, X-ray crystallography. And 250,000 is just a pretty small number as far as deep learning goes. Like, you really want it to be billions, or just like, every protein that there is. And I think that's just probably not possible to do with human labor. It could be extremely impactful to collect much more biodata and other areas of science too. So we talked about Vibe building a MacBook at home. I think this is the logical next step. Originally, this image, I had this as a ChatGPT generated image of someone with a laptop sitting on a hill overlooking a field with a lot of excavators. You could actually imagine something like this happening in the not too distant future. I don't know. A few years ago, you would not have been able to imagine sitting in front of your laptop vibe coding like an entire operating system or a C compiler or something like that. And now it's obviously very easy to imagine that. I think we're not quite there, but I think robotics is just a few years behind. But similarly, extremely large scale construction projects you could imagine very soon, even a single person or a small group of people being able to command a large number of resources. Speaking of large numbers of resources, so this is also at a fairly large scale. My friend Tapa a few years ago estimated how much it would cost to create a global power grid. The idea being that the sun is always shining very brightly on at least one desert in the world. And each one of those deserts in full could power the entire Earth's energy needs at that point in time. And so if you had a power grid that could connect all of these, that would just suffice. Like, you wouldn't need to think about storing energy. The number was fairly large. I actually think not intractably large. So with current technology, his estimate was $100 billion, which is like within range for what a government could do, or Elon or someone like that. But the idea of robotics is that you could imagine, cutting that number by a factor of 10 or 100, and then things that today seem just kind of intractable could become, actually totally doable for a startup. On the opposite end of the ecological impact spectrum, you could also imagine robots doing large-scale projects to restore ecosystems that maybe have been damaged. I think I would also put very large-scale carbon capture in this category as well. You could imagine trying to, figure out how many carbon capture devices and what's the cheapest way to actually just revert to the amount of carbon that was in the atmosphere before the Industrial Revolution. There's like a finite amount of robots that you would need to do this. And I think it's like unlikely that you would be able to do it with human labor alone, or at least the cost would be huge. This is the other Terraform. So software engineers in the room will recognize it as a software tool that allows you to declaratively state what you want a bunch of resources to look like, usually in the cloud. Usually this is like AWS instances or things that you want to be running in Kubernetes. As automation in the physical world becomes reliable and flexible and kind of able to make a lot of things in the physical world be certain ways, you could totally imagine having something like Terraform where you can just say, okay, this is the state that I want a factory room to be, or a hospital room to be in, or even the conference center. Like I want the state of the pathways to be clear so that people can walk through. And the robot's job is to run a control loop and make that be the case all the time. So the idea behind this one is that I think iteration speed is very important in a lot of areas of engineering. I think this is one of the reasons that software engineering goes very quickly, is that I can, I can write some code, I can test it, especially in web development, but in a lot of areas of software. Hardware generally moves more slowly. I've been very happy with the iteration speed that we have at our company. We can, design and build a new revision of our robots in a few weeks. But even that is, much slower than software. I think it's interesting to imagine as the degree of automation speeds up and as you approach the kind of physical speed limit of how quickly you can build something. You can imagine, here I have just a picture of the San Francisco skyline. You could imagine an architect kind of sitting here with this view, robots moving at maybe a few hundred miles an hour, kind of moving materials around, just sculpting maybe one of these buildings that the architect is allowed to modify till he gets, the profile just right so that it fits in well with the other buildings. Again, today this is like totally science fiction. Like this is not the world that we live in, but I think language models have shown us just that this can change very quickly. And I think that people should just start thinking about kind of what are the implications of robots getting very good and very flexible and existing at a very large scale. This one is science fiction. That Freeman Dyson, who was the source of the first two thought experiments, at one point in his career worked on something called Project Orion, which was a relatively short-lived project to make a nuclear spaceship that was powered by nuclear explosions that were here below this pusher plate. For some reason, this was more efficient than having some kind of continuous nuclear energy expulsion. But at any rate, their goal was to make a spaceship that was cheap enough to operate and flexible enough that a small group of people could kind of go in on building one and take it somewhere to an asteroid or a planet. And obviously today we think of any kind of manned space exploration as being this like intractably expensive thing that only governments can do. Even SpaceX is, maybe at some point they will do a private manned mission, but we don't really think of it as, being like a car that you can kind of take to Saturn if you feel like it. And that was their goal here. It seems, at least Dyson believes, that it's possible to do this within the laws of physics to make a spaceship that is that cheap. Here, I think we probably need to do some science first, but within our lifetimes, you could imagine there being, this kind of image of a single-family spaceship, just kind of a Jetsons title. Whoops. So again, on iteration speed, it's very important. It's also important in hardware. Usually, there's a human in that iteration loop. And right now, the human decision-making is very far from being a bottleneck. As the implementation of the ideas of the human engineer becomes faster and faster, you could imagine those human decisions becoming a bottleneck. At which point, if you want to keep going faster, I think you have to close the loop. And now you have an AI engineer that is making the decisions, and then robots that are implementing them. This probably makes the most sense to do in settings where you can test a lot of things in parallel, and each experiment is very cheap. This is kind of similar to the auto research concept that is becoming more popular in machine learning. You can imagine auto designing some physical product or piece of engineering for which you have one or more metrics that you want to maximize. People talk a lot about increasing GDP growth as a metric to optimize. I think this is actually not quite right. I think there are a lot of things that are not captured by GDP. One thought experiment there, which I think shows the misalignment between GDP and something like human values, is let's say that we have a relatively self-contained economy and all they make is robots. And the robots are made by robots. And so in the first year, there are 2 robots, and then the next year there's 2 robots manage to make another robot each. This is an economy with a very high rate of growth, but is just totally disconnected from anything that humans care about. Not anything, but many things that humans care about. Nonetheless, I think that thought experiment does get at one kind of quality that I think very high rates of economic growth will have, which is something recursive. People talk about recursive self-improvement for software, AIs. And I think very high rates of physical economic growth will have something of a similar flavor, where the work that we do this year makes the work that we do next year more efficient somehow. And so, if you want robotics to have a very high rate of economic growth, one of the things that you probably do have to do is have the robots this year help make more robots next year that will help automate more things the year after that. I said there were 14, but there are actually 15. And the last one is just these guys, which we've been looking at the whole time. These are our early robots for Pantograph. We're going to try running these here in these first 2 rows shortly. And if you're interested in driving them, I think we have too many people and not enough robots for everyone to be able to do that. But I don't know, whoever wants to the most can do that. The thing I wanted to say about these, in the spirit of the rest of the talk, is that a lot of people are trying to make consumer robots today. Usually they're pretty big, they're pretty expensive. They're something like the price of a car, 20, 25K. My guess is that the robots that will be most successful earliest are probably going to be pretty small, pretty cheap, something like the price of a laptop. That's what we're aiming for these. And probably not that strong. They have to be weak enough that if the models aren't very good, and the robot messes up and it does something crazy, that you're not going to completely destroy your house or hurt someone. And so this is what we're aiming for with these robots, something small and cheap and flexible that you can buy without too much trouble and move around. We're not saying anything too specific, but below the price of the most expensive laptop that you could imagine buying. Okay, maybe slightly more specifically, our BOM cost today is something like 4K. At scale, it'll probably be something like half that, and then we will add some margin on top of that. Sure. Yes.
Can you help us imagine what a robot like this can do? Like, can you use examples of?
Yeah, I mean, I think the nearest term one, most of these are very long term, but just the kind of home DIY. You can imagine trying to hook up a robot like this to a 3D printer and to a little lab where you have, glue and fasteners and, things that you might need to make little items around your house, or a new automated blinds opener or something. Yes.
a lot of your scenarios include recursive self-improvement, recursive self-reproduction. How far do you think we are from any sort of real takeoff from a robotics perspective on recursiveness?
I think things actually could move very quickly. Language models, it has taken a little bit, I don't know, maybe 6 years to get to the point that it feels like we're having RSI. I think with robotics, it could be faster just because we already know a lot of the techniques. We know how to manage big GPU farms. We know, what kinds of architectures train most stably at scale. And so my view is actually the main thing that is missing is just a good pre-training recipe. And if you can get that working at, medium scale, potentially 6 months later, you've taken it to frontier scale. And then you can have, a very high degree of capabilities. Yes.
Those robots that you're manufacturing right now, what do you see the ability that they have for stuff like household cleaning?
Yeah, I mean, obviously they're not that tall. They can probably clean your floor, but they probably can't make your bed. Once the capabilities are high enough that the models are reliable, then I think the right form factor is probably bigger. And again, maybe that doesn't take that long, but as long as the models just have some rate of error, I think you don't want a large error-prone robot that could hurt someone. Any last questions? Okay, one last question.
What kind of maintenance do your robots require?
Ooh, that's a great question. I am not the right person to answer that question. Hopefully very little, I think is the answer. Okay, so instructions for driving. All right, so these are Oculus Quest controllers. They have 2 different triggers on them. So there's a kind of index finger trigger and a middle finger trigger. If you pull the index finger trigger, that will close these grippers. If you, this joystick here on your left hand controls the treads. And then this last trigger, the middle finger trigger, while that's held, the robot will track the motion of your hands.
10 minutes.
All right, so we have 10 minutes for people to try driving robots.
You could make it 15.
Maybe I'll just pick up 2 things to show that it can be done, and then we can take maybe 4 people.
Yeah, and we'll just walk people through. It should be great, Jeff.
Yeah. All right, so maybe raise your hand if you want to. Okay, 1, 2, 2 more, 3, 4. Okay, great.
Real quick, can we get some proper driving?
Yeah.
Sure, yeah.
Back and forth action? Little Mo and Joe?
I was trying to do the cops, sorry.
Well, this is a little faster.
Oh, yeah.
Sit a juggle.
We've actually tried. We're working on it.
Does the Oculus serve any purpose, or is it just...
Yeah.
It is tracking the location of my hand trackers.
Whoa!
Great. So who do we have? Yes, Valerie and Ken.
Probably, it's so nicer to be, it sounded like far away from right now.
Yeah, we can have.
And can we do 2 at once, or just 1 at a time?
Yeah. This is bringing up our summit guy right now.
All right, here you go.
And she get her much and the power button.
Okay, that'll work.
Okay.
Um,
So, and you might want to stand back here. It's just a little bit easier for your brain to do the shape rotation.
Okay, so
Yeah, we slowly use.
Yeah, so that's your joystick. The right one doesn't do anything, only the left one.
Nice.
And then your index
So they're
finger.
very
is the
slow to
gripper.
the robot. So first try something like, yeah. And you want to make sure you match basically the plates of here to the plates of the gripper. And so that's a really nice way to constrain yourself back to the robot. And so then, yeah.
And then if you want your hands to be tracked, it's in middle finger gripper. While that's held, it'll track your every hand.
I see.
Nice.
Got it.
Oh. Has a Bert, do you want to bring a second person up for?
So over there.
All right.
These cups are bigger challenge.
Mhm.
All right. Cool. So, we'll do this over your head. And just be careful.
Could you speak to the hardest problems that you have to solve mechanically? Or maybe while people are...
Mechanically.
Yeah, I mean, like, what are the hardest problems in general?
Well, I don't know anything about the mechanical engineering. I think people are working on some grippers or something. We put a lot of work into the treads, which are the mobility system. They're a little bit more off-road capable than wheels.
And if you want to track your hand, and it's always in reference to here, so you get and walk whenever you're moving this, so you just hold the zero.
Anything interesting from our software side of things?
But we didn't wait until
On the software side, the main thing that we work on is pre-training. Searching for the best, most scalable method for learning a lot from video. Kind of the analogous modality for robotics is languages or code.
Can we make them like shake hands or something?
Yeah, it takes all ladies do. They also have different things than we do, quite a bit, so.
It's a little bit easier if you
Like get in the same orientation.
if you stand behind it and then also match the orientation of your hands to the orientation of the gripper before you hit the trigger. So if you let go of the middle finger and then
Oh, nice.
ooh yeah.
Hell yeah.
What's the best way to like orient it to the floor?
So yeah,
If I let go of the
If you let
tracker,
go,
will it
that's
still
the-
clip it?
and then-
As long if you hold this, it'll hold the gripper, and then you can let go of that, and then you can grasp and be like, yeah, nice.
then
Does it not go?
there's a lot-
No, and that's a turn limit there. So that's as much as he has mechanically on that turn. So yeah, this is a 6th off arm and the 7th off is like that's just like
Like,
Oh, how should you
like-
line it up?
should I try to go out from top down, you think? Or should I try to like
It's easiest if you just kind of go at it straight. Exactly.
Oh, hell
Exactly
yeah.
like that.
bring a battle bot? Exactly
So I would-
what? Exactly.
Like her arm was. Her left arm is just kind of straight down and that's the block.
and releaser.
nice.
Oh, sisterhood.
Yeah.
Do they have names?
Yeah.
Yes, of course they have it.
They do have names. Each revision of Robots, we've given a different theme of names. So the first revision was Shakespeare characters, Gloucester and Thisbe and Hamlet. And then these ones are physicists. So this is Van der Waals, and this is some physicists that it has shown.
Nice, nice.
Cool. Waterfall. One more person? Anyone else?
Anyone else want to drive a robot?
Great.
Okay, yes. Claire.
Oh, we got, I think, Pika? Just make
If you line up the
Right, and so first I just try the grippers and maybe try driving around a little bit.
So,
Gripper.
Nice.
that would be just
So we'll try to release arms. We'll just hit the clutch in there. That. Nice. Okay. Great. Nice. Nice. Bear it down.
This is so cool. And I'm. So this doesn't suit it, right?
Yeah, it is. That's hard to busy stage. We're gonna for depth right now.
Okay. I'm sorry, I missed the beginning of the session, but like